Knowledge of fire dynamics is critical for fire investigators to identify a fire's origin. Fire dynamics depends on the relationship of the fuel, heat, and ventilation to explain how fires start, spread, and interact with the structure. You could spend years studying fire dynamics, but in this course we want to focus on some key concepts that will help you better understand the impact of ventilation on fire damage patterns. In Greek mythology, fire has a practical, symbolic, and even elemental significance. Fire appears as both a creative, cleansing force and as a destructive, punishing one. We know that fire can be dangerous and deadly, but what is fire? It's not a substance or an object. Fire is a chemical reaction. Specifically, fire is an oxidation process, a gas phase chemical reaction that happens quickly, emitting heat and light. In the simplest terms, fire needs four elements to exist: fuel or combustible material, oxygen to sustain combustion, and enough heat to pyrolyze the material to raise the gases to their ignition temperature. Subsequently, an exothermic chemical reaction is needed to sustain flaming combustion. As a fire investigator, if you can determine where and when the three essential components of fuel, heat, and oxygen are available to react and support flaming combustion, you will have some ability to understand the movement of a fire through a structure. Heat starts the fire, sustains the fire, and spreads the fire. Thus, one way to better understand fire is to follow the heat. Heat is needed to increase the temperature of the fuel, cause ignition, and promote fire growth. Once a fire is started, it spreads by transferring heat energy in three ways: radiation, convection, and conduction. Radiation is the only method of heat transfer that does not rely upon contact between the heat source and the heated object. In this case, heat is transferred by electromagnetic waves. As a fire approaches the flashover stage, radiation becomes a significant mode of heat transfer. Radiant energy can be transferred only by line of sight and will be reduced or blocked by intervening materials. Heat shadowing can affect fire patterns and lines of demarcation. Convection is heat transfer through the movement or circulation of gases from the source of heat to a cooler area. Early in a fire, convection is a significant mode of heat transfer. The hot or superheated gases and the products of combustion spread into the upper portions of the room or area of origin, spreading the fire. For this reason, fire investigators may see soot or other products of combustion throughout a structure, even in rooms that had no direct flame impingement. Conduction is heat transfer through matter by physical contact. The ability of an object to conduct heat depends on its composition and density. The better the conductor, the more rapid heat will transfer. Materials like metal are excellent conductors. A metal beam or truss located in the fire compartment will absorb heat from the fire, and the temperature of the beam will increase. That beam may pass through a wall into another compartment. As the cooler end in the adjacent room heats up, it has the potential to ignite combustible materials in that room. The second fire may errantly lead fire investigators to identify two separate points of origin if the principles of conduction are not considered. Over the past 50 years, construction materials, construction methods, insulation, and furnishings have changed the means and the speed of fire growth within a structure. Today, residential structure fires are predominantly fueled by synthetic contents, which tend to have a higher heat of combustion than natural fuels. Let's look at an example. On the left, we have an older sofa. It is padded with cotton and has steel springs because the cotton padding doesn't hold its shape very well. On the right, we have a more modern sofa with polyurethane foam cushions. Flexible polyurethane foam is one of the most common materials in upholstered furniture today, with more than 1.7 billion pounds produced and used every year in the United States. You can already see that there is a dramatic difference in fire growth and spread between the two sofas. But why is this important to you as a fire investigator? Many of the first texts on fire investigation suggested that low burning and fire patterns on the floor were an indicator that flammable or combustible liquids were used within the fire. At the time, furniture was made from natural materials such as wood and cotton. But when modern furniture burns, the plastic melts and drips. The fire burns low, and sometimes we see what looks like a spill pattern. Understanding the differences in fuels commonly found in today's fires is critical to avoid misinterpreting the patterns left behind. In addition to being more flammable, synthetic materials generate more heat per pound than natural fuels. Within the first 3 minutes, the sofa with the polyurethane foam cushions hit a peak heat release rate of almost 5 megawatts. That is more than twice the energy needed to flash over a residential scale room with an open door. The cotton sofa also releases a significant amount of energy, but as you can see, it does so over a much more extended period. The peak heat release rate of the cotton sofa never climbs above 300 kilowatts as it burns steadily for nearly an hour. The heat release rate of the synthetic sofa is typical of the furnishings found in many homes today. When a fuel burns, its chemical composition changes, resulting in the production of new substances and a release of energy in the form of heat. In the case of complete combustion of a hydrocarbon fuel and oxygen mixture, everything is burned, producing only water vapor and carbon dioxide. When the oxygen supply is limited, combustion is incomplete. Smoke is a byproduct of incomplete combustion. In a typical fire situation, smoke is a visible, flammable, heated suspension of solids, aerosols, and fire gases that are toxic, flammable, and volatile. Extinguishing a burning candle produces a column of smoke that, under careful observation, can be seen to burn back to the candle wick, demonstrating that smoke is an ignitable fuel. Click the icon to view an example, or click Next to proceed. In this experiment, we ignited a small wood crib in a plywood box. In the early stages of fire development, the elements of the fire tetrahedron were in balance, and we see flames around and above the crib. As the crib-fueled fire heated the plywood box's walls, the amount of gaseous fuel being generated increased and started to burn. The increased burning decreased the amount of oxygen available inside the box to the point where the flame self-extinguished. In other words, the oxygen concentration dropped well below 15%, meaning there was not enough oxygen to support gas phase combustion, or in other words, to produce flames. Oxygen supports the chemical processes that occur during a fire. As previously noted, when fuel burns, it reacts with oxygen from the surrounding air, releasing heat and generating combustion products. It is essential to understand how the components necessary for combustion are transported through a compartment or a structure if you're going to analyze a fire based on when and where the fuel, heat, and oxygen coexist. Typically, a compartment fire model has been used to describe how a fire entrains air and consumes the oxygen in a chemical reaction, resulting in the generation of heat and the loss and distribution of mass from the fuel. The heated gases generated by the fire are less dense than the surrounding air. As a result of this buoyancy, these gases rise to the top of the compartment. Once the gases impact the ceiling, they flow across the ceiling, forming a ceiling jet. As the gas's temperature increases, they expand and flow under the ceiling until the ceiling jet reaches the walls of the compartment. The walls constrain the hot gas flow, causing a hot gas layer to form. As the fire's heat release rate increases, the depth of the hot gas layer will increase. If the door to the compartment remains closed and there is no other oxygen source, the fire will begin to decay and may self-extinguish. If the compartment's door is open, the hot gases will escape through the upper portion of the door, while fresh air flows into the compartment through the lower portion of the door. This influx of oxygen will cause the fire's heat release rate to increase, and flashover will likely occur. Flashover is a transition phase in the development of a compartment fire in which surfaces exposed to thermal radiation reach ignition temperature more or less simultaneously. Fire spreads rapidly throughout the space, resulting in full room involvement or total involvement of the compartment or enclosed space. In some situations, flashover may be caused by opening a vent, such as when the fire department attempts to ventilate the structure, or when a window fails due to thermal stress. Click the icon to see an example. A firefighter approaches the window of an apartment that appears to be full of smoke. As the window is broken, air from outside the apartment flows into the building. The oxygen mixing with the hot fuel gases rapidly transitions into flaming combustion. The circulation of fresh air and smoke is referred to as the flow. A flow path is the volume within a structure between at least one inlet and one outlet that allows heat and smoke movement from areas of higher pressure to areas of lower pressure, accessible via doors and window openings. Several flow paths may exist within a structure based on varying building design and available ventilation openings such as doors and windows. Ventilation openings are the beginning and end points of a flow path and can be unidirectional or bidirectional. When the flow is moving in only one direction, the vent is considered unidirectional. When a single ventilation opening serves as both an intake and an exhaust, the vent is bidirectional. A unidirectional intake vent indicates an exhaust vent somewhere else in the structure, usually at a higher elevation. Similarly, a unidirectional exhaust vent is an indication that there is an inlet somewhere else in the structure. The intake and exhaust portions of a bidirectional ventilation opening are separated by the neutral plane. The neutral plane indicates the level where the pressure on the inside of the compartment is equal to the pressure outside the compartment and suggests the extent of fire development. If the bidirectional ventilation opening is the only opening, the intake portion of the opening will become smaller as the fire grows and approaches flashover. It is possible to have both unidirectional and bidirectional ventilation openings in a single compartment. Thus, the relative position of intake and exhaust ventilation openings are critical to determining the flow path because of the buoyancy of hot gases. The air movement around and through these open ventilation sources, especially bidirectional ones, has a strong influence on burn pattern development. Let's take a look at an example. In this case, the door is serving as which type of opening? The door is a bidirectional vent opening. Smoke can be seen flowing out the upper portion of the doorway, while fresh air is flowing in through the bottom portion of the doorway. The fresh air reaching the fire is limited by the size of the ventilation opening and the extent to which that opening is serving as an exhaust vent. Where would you expect to find flaming combustion? Let's watch the rest of this experiment. How much of the room is involved in flaming combustion? Has the room transitioned through flashover? Correct. This fire has transitioned through flashover. Traditionally, fire behavior is explained using this fire development curve. This ideal curve is best suited for describing a fuel-limited fire. In other words, a fire that has all the oxygen it needs to sustain the heat-generating chemical reaction with the fuel. Thus, the fire's growth is constrained only by the available fuel load. There's enough oxygen available for all fuels to burn at their maximum rate. In fuel-limited conditions, a fire typically has a growth stage, a fully developed stage, and a decay stage. The growth stage occurs as fuels ignite throughout the compartment, causing the fire to spread and intensify. When fully developed, available fuels are burning at their optimum rate. As those fuels are depleted, the fire enters the decay stage and its temperature begins to drop. In a fuel-limited fire, where oxygen is plentiful, fire pattern development is primarily driven by the location of the fuel packages as well as the material composition of those fuels, because it is the availability of fuel that controls the intensity of burning. In these conditions, the fire typically spreads from one fuel package to another through contact and radiative heat. Click the icon to see an example or click Next to proceed. This upholstered chair is the only combustible in this room. The room has an open doorway. The peak heat release rate of the chair is less than the ventilation limit of the doorway. Therefore, the fire size and the heat generated is limited by the amount of fuel that can burn in the air. The fuel-limited fire development curve is not a fair representation of how fires develop when confined in structures. Most fires will become ventilation limited before fire suppression operations are initiated. This is mainly due to modern construction practices, materials, and the amount of fuel in the structure. As a result, you may not encounter many fires as a fire investigator that remained in the fuel-limited stage. This graph is a more accurate representation of fire development in a compartment. In a ventilation-limited fire, the fire's growth is constrained by the amount of available oxygen. There is more fuel available to burn than there is oxygen to sustain its combustion. In ventilation-limited conditions, a fire typically has a growth stage and then an initial decay stage. If a change in ventilation introduces additional oxygen, the fire can proceed to a fully developed stage and then a decay stage. In ventilation-limited conditions, the growth phase occurs as fuels ignite throughout the space, causing the fire to spread and intensify. The fire quickly depletes the available oxygen and begins to decay even though more fuel is available. If a change in ventilation introduces additional oxygen into the compartment, the fire can grow again and reach the fully developed stage. All fuels are burning at their maximum rate. The fire will transition to a second and final decay stage as the fuels are depleted. Fire temperatures drop accordingly. Click the icon to see an example or click Next to proceed. Here we will compare a fire in a furnished room with an open door to a fire in a similar room with a closed door. Both fires begin as fuel-limited fires. The synthetic fuels burn inefficiently with the oxygen that makes up 21% of the air. As a result, smoke-containing fuel is generated and begins to collect at the ceiling of each compartment. In the room with the open doorway, smoke flows out of the top of the opening and fresh air flows into the lower portion of the opening. This airflow supplies oxygen to the fire. In the room with the closed door, the hot gas layer, which has a reduced amount of oxygen, grows and begins to interfere with the combustion zone at the top of the flames. The air in the closed room at the start of the fire is the only oxygen source for combustion. As a result, the size of the fire is decreasing as the hot gas layer descends toward the floor. Once the amount of oxygen in the room is reduced to less than 15%, the flaming combustion in the closed room stops. The fire in the open room continues to grow as more fuel becomes involved. The hot gas layer begins to interfere with the flaming combustion zone, which results in the hot gas layer gaining additional unburned fuel and energy. Even with the open door, the fire is starting to be limited by the lack of adequate ventilation. Once the amount of fuel and heat in the hot gas layer is sufficient to support combustion and mix with sufficient amounts of oxygen, the hot gas layer begins to burn. This starts the transition through flashover. The increase in radiant and convected heat generates additional fuel via pyrolysis. As the additional combustion products and pyrolysates fill more of the open doorway, the air being entrained through the lower portion of the open doorway gains speed. Even so, the fire in the room becomes more vent limited until finally the excess hot gases start to burn on the exterior of the room as the flaming combustion inside the room moves closer to the source of the oxygen coming in through the open doorway. Now that you have reviewed the key concepts of fire dynamics, you are ready to proceed to the next module.